So good day, everyone. Today, welcome to our fourth webinar in the FEBio Studio webinar series. This webinar today is on biphasic materials. And I would like to present to you a little bit of background on biphasic theory so that you better understand how we implement those in FEBio Studio. And then I will show you a few slides that show, results, but also I will have like a demonstration of unconfined compression stress relaxation in FEBio Studio. So let me turn on my laser pointer here. My name is Gerard Deteshian. I'm a professor of mechanical engineering at Columbia University. So biphasic materials are mixtures of a solid and fluid. So we use biphasic materials to do porous media theories. Biphasic materials are implemented in FEBio, and here are some of the things that you need to know about this implementation. We make the assumption that the solid matrix is porous and permeable, meaning the fluid can flow within the porous matrix. And the solid skeleton of the solid matrix is intrinsically incompressible. So if you were to drop a biphasic material at the bottom of the ocean, then it wouldn't change volume because, the solid matrix is incompressible, and the fluid is also assumed to be intrinsically incompressible. But the pores are compressible, so you can actually gain volume or lose volume by compressing the pores, and that's the important thing. The change in volume that occurs in a biphasic material is due to the change in the pore volume. So to describe a biphasic material, we actually then have volume fractions, so we can apportion a fraction of the mixture to the solid and a fraction to the fluid. These volume fractions are denoted by Φs here and Φf here, and they satisfy this saturation condition that Φs plus Φf is equal to 1. So you only need to specify one of them in a particular analysis. Here I'm showing you just a regular kitchen sponge being squeezed. In this case, the fluid is obviously air. And what you can see is during this compression, which I'm going to stop the animation, we don't need to have it going for so long. You can see that the pores are changing in volume. And what you can see is that there's very little lateral expansion, of the sponge. So if you were looking for a Poisson ratio effect, you would see that there's hardly any Poisson ratio expansion, right? So this, I want you to understand, is very representative of what a biphasic material is. But for biological tissues, the pores are very small. However, they can occupy a large fraction. So the porosity is given by Φf. So the porosity could easily be 80%. In some cases, it could be up to 90%. And so that's the basic, description of a biphasic material from a physical perspective. How are biphasic materials implemented in FEBio? So basically what you need to know is that we neglect inertia terms in the current implementation of biphasic materials. So inertia terms are only needed if you want to do wave propagation analyses in porous media, such as ultrasound waves propagating. So what we're going to do is solve the quasi-static momentum balance equation. What kind of viscosity do we have in a biphasic material? Well, there's three kinds. You can have that the fluid is viscous, which means that there's friction between fluid molecules. You can have that the solid is viscous, which means it's an intrinsically viscoelastic solid matrix. And the dominant form of friction that we assume in a biphasic material is that there's friction between the fluid and the solid. Now, it's easy to do dimensional analysis and for biological tissues, and we find that the friction between fluid molecules is going to be negligible compared to the friction between the fluid and the solid. So in a strict sense, therefore, there's no term, there's no material parameter for the fluid viscosity in a biphasic material. Another assumption, which is not of major consequence, but I need to mention it, is that any body force that's acting on a biphasic mixture is assumed to be the same for the solid and the fluid. And the best example is gravity. And you might ask yourselves, why would there be an option to apply different body forces and different constituents? The answer is the general mixture theory allows it. It becomes useful, for example, when you actually have ions in your mixture and they're subjected to an electric field, in which case negative ions will go in one direction, positive ions will go in an opposite direction. And that's a case where the body forces are acting in different directions. But that doesn't occur in a biphasic material. And finally, when we derive the equations, we're only solving the mass balance and the momentum balance. We don't solve the energy balance because we're going to assume that the temperature remains constant. So there are no temperature changes, which means we cannot do heat conduction, just like the structural mechanics module, where, which is not a thermoelasticity module, it's just an elasticity module. It's the same with the biphasic module in FEBio. So what happens when you load a biphasic material? The most obvious thing is that the interstitial fluid will pressurize and it'll flow. It'll flow from the high pressure location to the low pressure location. This flow is resisted only by friction between the fluid and the solid, because remember, there's no inertia terms. Now, even though there is friction between the fluid and solid, in a strict sense, friction is dissipated into heat, but the frictional heat is not modeled explicitly. We simply assume that it radiates out of the tissue to maintain a constant temperature. The same is true in elasticity or viscoelasticity rather. So the standard viscoelastic material in the structural mechanics module of FEBio also does not have any associated temperature change when you look. Here's an example of a sponge, which is a biphasic sponge being squeezed on the side. And what we have is we are modeling only a single octant of the sponge, and then I'm using the symmetry planes in FEBio Studio to display the entire sponge, just for fun. And in this particular case, I can show you the fluid pressure and the fluid flux. So the fluid pressure is actually 0 on the outside boundary because that's actually the boundary condition that I want. But when I squeeze the sponge from the side, then I can see the fluid coming out. If I turn my view in a different direction, I can see that the inside of the sponge is pressurizing. So this is just illustrating how the fluid pressurization is occurring inside, but on the boundary, I've prescribed ambient conditions, so it's like 0 pressure. Another problem that we're going to look at more closely is unconfined compression stress relaxation. So you have this disk, which is quarter disk here, and we're prescribing a compressive strain. We're going to reduce the height of the disk by exactly half of the thickness. And you saw that it pressurized and the fluid started exiting, but after it squeezed sideways, right, it expanded sideways initially, but as the fluid squeezes out slowly, then the solid matrix, which is porous, recoils. And for the material properties that I picked for this model, the solid matrix recoils completely back down to the initial radius, but that's just because I picked the Poisson ratio of 0, just like that sponge that I showed you in the second slide. But what happens is, because the fluid pressure is transient, if I look at the stress acting on the top face, then I integrate that stress over the surface area, then I get a load. The load response during the compression, which is very quick, I'm compressing in 1 second, the load increases very fast, but as the fluid depressurizes and as the fluid squeezes, the load recovers. This type of load relaxation is typical of a viscoelastic response. But even though in this case, the solid matrix is elastic, but we call this a flow-dependent viscoelasticity. It comes from the friction dissipated between the friction between the fluid and the solid, which is dissipated into. So in this particular example, I'm illustrating stress relaxation. I could have done a creep problem, but for this presentation, I'm going to focus on stress relaxation. In a moment, after I show you a few more slides to explain the biphasic theory, I'm going to do this problem, this unconfined compression problem, in front of you using FEBio Studio. So that'll be a direct demonstration of this one. So let's take a quick look at the theory. So in a biphasic material, you need to have a variable to, that measures the fluid pressure. So because we assume that the fluid is intrinsically incompressible and the solid is intrinsically incompressible, there is no function of state like in an ideal gas law, which relates the pressure to the volume. In an incompressible mixture framework, P is a Lagrange multiplier. So that means we have to solve for it directly. So it turns out this will become one of the unknowns in our differential equation. We also have stress in this porous solid matrix. We're going to denote the stress with the symbol sigma E. The letter E usually means effective stress. Of course, if you choose the material to be elastic, you can think of E being elastic, but the material could also be viscoelastic, which means the solid is intrinsically viscoelastic. You have friction within the solid as well. So this stress is the stress response of the whole porous matrix. It's not the stress strain response of the skeleton material. So if, let's say, I had a porous aluminum, this would not be the constitutive relation for aluminum. It would be the constitutive relation for that specific porous aluminum. Whatever that pore structure is, that will be the stress strain response. That's important to understand. So we relate the stress to the deformation gradient F, and from the deformation gradient, we can evaluate any measure of strain that we want in the finite deformation regime, and of course in the limit of small strains as well. The total stress in the mixture is also called the mixture stress. B is the sum of the fluid pressure contribution, which is hydrostatic, which is why you have the identity tensor here, and this stress in the solid matrix. Importantly, the fluid pressure is positive in compression by convention. This is true in mechanical engineering and most field of mechanics, although in chemical engineering, occasionally they switch to convention. But in FEBio, the pressure is positive in compression, but the stress is positive in tension. So keep that in mind. And then, of course, if you have a biphasic material, you need to worry about the flow of the fluid relative to the solid. So this is the velocity of the fluid. It's a variable that I introduce here just to clarify the meaning of the fluid flux, but we actually don't solve for the fluid velocity. We subtract from it the solid velocity, that would be the relative velocity, but then we multiply it by the fluid volume fraction, which also turns out to be the area fraction. So if you have a mixture area, elemental mixture area dA, then phi F dA is the fluid area. So the fluid flux is therefore the amount of fluid that's flowing through the pores. So this is the fluid flux, which is one of the unknowns in our biphasic field. So it's important to understand the meaning of it. So the advantage of using the fluid flux is that when you take the normal component along this surface normal, multiply it by the elemental area, then you get the volumetric flow rate through the mixture area. That's why you need to multiply by the porosity. So I defined to you what are the unknowns that we have. Now let me summarize the governing equations. So I told you earlier that we solve for the mass balance equation and the momentum balance equation. We don't solve for the energy balance because we assume isothermal conditions. So it turns out that the only differential equation we need to solve for mass balance is the mixture mass balance. The divergence of the solid velocity plus the fluid flux is 0. Let me explain what this means. The divergence of the solid velocity is related to the rate of change of the solid volume. And the divergence of the fluid is like the concept of fluid divergence in fluid mechanics as well. So, a fluid that's doing this is diverging, a fluid that's doing that is converging. So if, let's say, the divergence of the solid is negative, right? If the divergence of the solid, that means the solid is losing volume, then the fluid divergence of W is positive, right? If divergence of the S is negative, divergence of W is positive, which means the fluid is actually squeezing out of the pores. So it's diverging, right? So it's a positive divergence and vice versa. So this essentially mixture mass balance says that whenever you reduce the pore volume, you're going to also lose fluid. Whenever you increase the pore volume, you're going to gain fluid. That's what it says. The mixture momentum balance, well, if you neglect the inertia terms, this is Newton's second law of motion, sum of forces equal to 0, and the divergence of sigma comes from the sum of surface forces. So this particular form of the equation is valid in the absence of body forces. I'm not going to demonstrate any examples with body forces today. So the divergence of the stress is equal to 0. That's the equation that we're solving, but this is the mixture stress. The mixture stress, remember, has a contribution from the fluid pressure and this elastic stress. So that means that when you rewrite the divergence of sigma and substitute this expression for the mixture stress, you end up with the minus gradient of P plus the divergence of sigma equal to 0. Here's the description of how you specify biphasic material in FEBio. So I want to show you the meaning of the quantities that appear here in relation to the governing equations. So the stress strain relation for the solid, for the porous solid matrix is the solid constitutive model that you pick here. So in this particular example, it's the Navier-Stokes model. So this is sigma E, happens to be a Navier-Stokes in this case. Now, there's two constituents in the mixture, so you need two equations of mass balance. You could have one for the fluid, one for the solid, or one for the mixture, one for the solid. Turns out that the mass balance for the solid can be integrated exactly, so it's no longer a differential equation. It's an algebraic solution, which is given here. It tells you that the volume fraction of the solid in the current configuration can be obtained from its value in the reference configuration divided by J, where J is the determinant of F. So phi-RS is the referential solid volume fraction. It's the quantity that you specify here. You see phi-RS. So a value of 0.2 means 20% of the mixture consists of a solid, by volume, and therefore the porosity is 0.8. It's 80%. And then we need a constitutive relation that relates the fluid flux to the gradient of the pressure. Remember, the fluid flows from high pressure to low pressure. So the gradient of the pressure is positive from low to high. The negative sign means from high to low. So, and K here is a material function called the hydraulic permeability tensor. And this relation that you see here is known as Darcy's law, but it also is reproduced from the mixture theory equations. In this particular example, the constitutive relation for K is given in this category called permeability. This example, I picked an isotropic tensor, which is constant. This does not vary with porosity. So let me stop here because there are many people who ask questions on the forum about the meaning of phi-RS, and often they say, I change this value, I see no effect on the solution. Why is the case? The answer is phi-RS does not show up explicitly in this governing equation, nor does it show up explicitly in this governing equation. So neither in the momentum balance nor in the mass balance. So the reason why it doesn't influence the solution is because you're neglecting body forces. The only time, there are two places where phi-RS will have an influence. Either you include body forces, in which case the density of the apparent density of the fluid and solid will depend on the volume fractions, or if you decide that your hydraulic permeability depends on the porosity. As the tissue becomes less and less porous, as you squeeze out the fluid, the porosity goes down. You could say, experiments show that the permeability should decrease. So if you pick a constant, permeability that doesn't change with porosity, then this parameter has no influence. You could put any number you want here. But if you decide, on the other hand, that you want permeability that depends on the porosity, then this is the place where you specify the porosity. So I just want to make that very clear. Okay. Boundary conditions. So now we understand that, we have two differential equations that we need to solve, the mass balance for the mixture, the momentum balance for the mixture. And so we're going to solve for two unknowns, which are the solid displacements, which is a vector, and the fluid pressure, which is a scalar, which is good because the mass balance is a scalar differential equation and the momentum balance is a vector differential equation. So I have enough equations to solve for these two unknowns. So it turns out that the solid displacement and the fluid pressure are what we call the nodal degrees of freedom. These are the unknowns that FEBio is going to solve for. When you solve these differential equations, you need boundary conditions. And in the field of partial differential equations, there is a concept of Dirichlet boundary conditions, which are boundary conditions on the unknowns. In the field of finite element theory, we call these essential boundary conditions. These are the boundary conditions that you apply on the nodal degrees of freedom. So you could say on the boundary, I want to prescribe the displacement. Let's say I don't want this boundary to move. I will fix the displacement. Or I want the boundary to be free draining. I want to allow the fluid to escape. So then I can prescribe the pressure P on this boundary. Conversely, you can have, Neumann boundary conditions, which are boundary conditions on the derivatives of your unknowns, of your unknown variables. In the finite element field, these are called natural boundary conditions. So the natural boundary conditions, if you take the spatial gradient of the displacement, you can evaluate the deformation gradient and therefore the strain. You take that strain and you plug it back into the stress-strain relation, and then you end up with the stress, the elastic stress or the effective stress. And then you add to it the pressure term, then you get the mixture stress. and then you project it along the normal to the boundary, you get the mixture traction. Okay, so this mixture traction is related to the gradient of the displacement, and also it's related to the pressure. And you also can evaluate the gradient of the pressure, plug it back into Darcy's law, and you can evaluate the flux. You project it along the normal to the boundary, and this becomes the natural boundary condition for the fluid flux, is the normal component of the fluid flux along the normal to the boundary. So natural boundary conditions are the default boundary conditions when you prescribe nothing on a boundary. Let's say there's this entire boundary, you didn't prescribe the displacement, you didn't prescribe the pressure. So what does the finite element code assume? It assumes that it's a traction-free boundary, so T is 0, and Wn is 0, which means it's an impermeable boundary. So that's an important point that you need to understand. If you don't specify anything on a boundary, it is by default an impermeable boundary. That's what happens in a biphasic material. Okay, now let's take a look at the specific example, which I'm going to illustrate in a moment in FEBio Studio. So what I'm going to do is I'm going to show you unconfined compression stress relaxation of this disc with impermeable frictionless flatness. So all of these are keywords. So unconfined compression means I'm going to prescribe, stress relaxation means I'm going to prescribe the displacement. And impermeable means I want no fluid flux normal to the surface on which the platens are acting. And they're frictionless. That means no tangential traction, zero tangential traction. So what are the essential boundary conditions? Obviously, at the bottom face, I don't want it to move. So the bottom face is the one that's underneath this line here. I want UZ, the displacement in the Z direction, to be 0 at the bottom face. And at the top face, I want to prescribe the displacement. I want to compress it by 50% of its initial thickness in 1 second, right? So I prescribe it using this, a load curve for U0 as equal to H. I also want the lateral boundary to be exposed to the bath, to ambient conditions in the bath. So I want the fluid pressure to be 0 because this is a gauge pressure. So at R equal to R0, I need to prescribe these 3 boundary conditions explicitly in the finite element code because they're essential BCs. The natural BCs, I use a different color font, simply implement the rest of the conditions that I told you that we have. Frictionless in the traction components in the tangential direction, so in the radial direction and in the circumferential direction, that's TR and T theta, and 0 fluid flux in the direction normal to the surface because the platen is impermeable, and the same natural boundary conditions apply on the bottom surface here. And on the lateral surface, it's a traction-free lateral boundary. It can expand freely. There's nothing that prevents, there's no pressure applied, no traction, no shear stress. So all 3 components of the traction are 0. I don't need to prescribe these explicitly because they're natural BCs, okay? Now, in this particular case, I'm making use of symmetry planes. So in addition to these essential boundary conditions, I will need to say that the displacement normal to this face is 0. The displacement normal to this face is 0. So this is the model I'm going to implement just after I explain the last thing here before I go to FEBio Studio. So now we're ready to run our FEBio analysis. I want to display the results. I want to relate the plot variables that are available to you in FEBio Studio to the names of the variables that I've been using so far. So when you request to plot the displacement, you're looking at the components of the vector of the displacement vector U. When you request to plot the relative volume, you're looking at J, which is the determinant of F. The stress is in fact the mixture or total stress. It's the sum of these 2 terms. It's important because the stress variable is also used in the structural mechanics module. So we don't say total stress, we just call it stress. The effective fluid pressure is the pressure that we solve at the nodes. This is the essential variable, so the finite element solution for the pressure. But when you evaluate the mixture stress, you evaluate it at integration points of the element. And because this effective stress is evaluated at integration points. So somewhere in the code, at some point, we also need to evaluate the fluid pressure at the integration points. If you want to display that, we call it the fluid pressure variable. So it's the fluid pressure at the integration point of the elements, which in the plot file, they're average over all the integration points. So there's one single value of the pressure at each element. The fluid flux is W, the porosity is Pf, and the solid stress, even though we call it solid stress, it's really this effective stress. It's important to understand. Now, by default, when you select the biphasic analysis, it'll include displacement, stress, effective fluid pressure, fluid flux, and solid stress. So we need to explicitly add relative volume, fluid pressure, and porosity if we want to include those in a particular analysis. So now I'm going to switch to FEBio Studio. I'm going to launch it. And I'm going to demonstrate to you how we can run this particular analysis. So I'm going to launch FEBio Studio, and I'm going to create a new model, and I'm going to request a biphasic analysis. And what I'm going to do is I'm going to create or build the geometry. Oh, before I do, I want to select my units. So I'm going to go to Preferences, and I'm going to pick my units. For the current model, I want them to be millimeter Newton second. So all the dimensions that I specify for the geometry will be in length in units of millimeters. And the forces that I will calculate will be in newtons. And therefore, the pressure will be Newton per millimeter squared, which is megapascal. I want you to remember that because I'm going to specify material properties that require knowledge of the units. Now I'm going to create the geometry. I'm going to use this wedge geometry. I'm going to have it have a radius of 2 millimeters and a height of 0.5 millimeter. And I'm going to take the default angle of 90 degrees, and I have my wedge geometry. Now I'm going to mesh it. And I'm going to start out by saying I want 16 slices. It's like a pizza slice, you know, so the slices are in the direction, in the radial direction. The segments are in the circumferential direction. I want 20 segments. And the stacks are in the vertical direction, the thickness direction. Because they're frictionless splatins, I only need one element through the thickness because there's going to be no variation of the strain in the axial direction. I'm going to say apply for now, and I create this nice uniform mesh. So I have now created the geometry and I have meshed it. So I'm ready to save this. I'm going to save it, put it on my desktop, and I'm going to call it unconfined compression. I see, I can't type. Stress relaxation, I'll abbreviate that. I'll put that here just to be on the safe side in case, my computer crashes. So now I'm ready to create a biphasic material. So I'm going to come to the material entry in the model tree, and I'm going to right click and I'm going to say add material. And under the category, I'm going to say bi, tri, multiphasic, and then I'm going to click on biphasic material. Now I'm ready to pick a solid material. I'm going to make it Neo-Hookean. And then a permeability. So contrary to the example that I had in my slide, I'm actually going to create a Holmes-Mao permeability material, and then I'm spend some time describing what that is. And the solvent supply is an optional material, which is only if you want to have like a source of fluid. Let's say you have a vascularized tissue, and through the vasculature, there's like fluid permeates through the microvasculature, and therefore you want a supply of fluid inside your material, but that's a special case. So I'm going to now specify the material properties. Even the volume fraction, I'm going to pick it to be 0.2, solid volume fraction. So 20% of the mixture volume is the solid. Fluid density is not 1 ton per cubic millimeter, but because I'm not applying body forces and I don't have inertia forces in a biphasic analysis, I am not going to change this value because it has no effect. For Young's modulus, I'm going to select 0.5 megapascal because that's the typical value for articular cartilage, which is my field of research. And Poisson's ratio, remember, is Poisson's ratio not for the response of the tissue early on, but after the fluid has escaped, just like that sponge movie I showed you, because it was air in the sponge, you could see that it did not expand laterally. So I'm going to make that assumption and just use 0 for the Poisson ratio of the solid. For the permeability, the hydraulic permeability, a typical value for articular cartilage is 10 to the negative 3 millimeter fourth per Newton second. What's the meaning of M? What's the meaning of alpha? So here's an opportunity for me to actually, go to the help menu and launch my browser to go to the knowledge base. We're going to look up the meaning of the Holmes-Mao, material. And I go to the manuals, and I'm going to open up the user manual. Now, I could search for the Holmes-Mao material here, but I'm not going to do that. I'm simply going to go to the chapter on materials, and then I'm going to go to biphasic materials. I'm going to scroll down, and I'm going to look up permeability materials. And out of these, here's the Holmes-Mao material. I'm going to click on this, and you can see a description of the material parameters. So what I entered is K0, which is the hydraulic permeability in the reference state. Now I need to figure out, do I want to specify a non-zero value for M and for alpha? So what are M and alpha? So what we're saying is, in this particular material model, the hydraulic permeability could decrease as you compress the tissue. As J becomes smaller than 1, that means you're losing volume in the pores. And so you multiply this J squared minus 1 by this non-dimensional parameter M to model an exponential decrease of the permeability with M. And if you want to take into account the porosity, you could also have a non-zero coefficient alpha, in which case the value of phi0 or phi rs has an impact on the solution. In my case here, I'm just going to pick a non-zero value for M, but I'm going to keep alpha equal to 0. So in the end, the porosity is not going to have an influence on this particular model, but if I pick the non-zero value for alpha, it would. So I'm going to come here and I'm going to pick a value of 6, which is a large value, but it's representative of how much cartilage actually the permeability decreases as you lose pore volume. And that's it. So I'm going to save this, and I'm going to assign this material to the geometry that was already selected by clicking on the plus sign here. So now I have defined my material, and I have defined my geometry and mesh. So I'm ready to apply the boundary conditions. Okay, so to apply the boundary conditions, let me just move my Zoom window. To apply the boundary conditions, I'm going to select this face here, and I'm going to turn off the mesh, and I'm going to apply the boundary conditions more or less in the order that I showed them in the slide. So I'm picking the bottom face, then I'm going to go to physics, and I'm going to say add boundary condition, which is the top one. But from then on, I'm going to use this keyboard shortcut. So for now, I'm going to do it this way. Fixed displacement is the first entry, and I want to prevent displacement of the bottom face along the Z direction. Then I'm going to come to the top face, and I'm going to do the same thing, but I'm going to use the keyboard shortcut. And instead of fixed displacement, this time I'm going to have a prescribed displacement. And I'm going to have a displacement along the Z direction. And remember, I want to compress the tissue by half of its initial thickness. So I'm going to put 1/4 millimeters. And the negative sign is because I want to go in the downward direction, so in the negative Z direction. Okay, so that completes this boundary condition. And then I'm going to go ahead and apply the essential boundary condition on the fluid pressure here. I'm going to say 0 fluid pressure on the lateral boundary. And you have to remember to click this box here, otherwise this boundary condition will not be active. And then I'm going to save. So I'm done applying the essential boundary conditions that were in the slide. But remember, I told you that because we have symmetry planes, we also need to prevent displacement of this face in the direction normal to it, which is the X direction. So I'm going to fix the direction along X for this face, and then I'm going to fix the direction, the displacement along Y on this face. So I am done applying boundary conditions. Now what I would like to do is double check that I actually am applying this displacement in the time frame that I want. The default load curve says that the displacement that I prescribe, which is -0.25, will be scaled from 0. You see down here, it says 0 and 0. It's going to be scaled from 0 to 1 at time 1, which means I'm going to apply the compression in 1 second. And this load curve will multiply the value of -0.25. And I'm satisfied that the default value is the correct one. So I'm going to keep it. So I'm now ready to tell FEBio that I want to perform a biphasic analysis. So I go to physics and I say add an analysis step, and I select the biphasic analysis step. And I say, okay. So now I want to decide how long do I want my analysis to run. If you remember, I showed you the stress relaxation curve in one of my slides. You probably don't remember the details, but actually it took almost a little bit more than 50,000 seconds to reach steady state, to have the fluid pressure go down to 0. So, and because I'm ramping up displacement in 1 second, I do want my time increment to be 0.1 second by default. This way I can accumulate about 10 time increments during the loading phase, which is very rapid. I don't want to load in 1 second in one single step. So that means that if I want 50,000 seconds, I need 500,000 steps that are 0.1 seconds long to give me a total analysis time of 50,000 seconds. The maximum step size, the default here is also 0.1 second. And of course, if I did that, that means I would have to run 500,000 time increments, but I'm not going to do that. What I'm going to do is I'm going to click on this box here that says use must points, and I'm going to allow my analysis to increase the time increment as time progresses. Okay, and I'm going to explain that as we go. I'm going to do a few more changes. So the governing equations of a biphasic analysis produce a non-symmetric stiffness matrix. But the default analysis for biphasic is symmetric only because if you do small strains, the symmetric solver does a really good job of solving the analysis, and it does it faster because you have fewer terms in the stiffness matrix than non-symmetric. But we're not doing a small strain analysis here. Remember, we're compressing by 50%. So I should definitely pick the non-symmetric matrix symmetry. Now I'm going to, because I picked the non-symmetric matrix symmetry, I need to change the quasi-Newton method from BFGS to Broyden, because the BFGS method is specifically written for symmetric stiffness matrices. As of now, you have to do this manually. And then these are the default settings for maximum reformations, maximum updates for this quasi-Newton method. I'm going to keep everything here to be the default at this point. I feel like I've done enough changes. The only thing I need to worry about now is the fact that I checked this box that says use must points, which means I'm not going to rely on this maximum step size, which is entered as a single value here. I'm going to create a load curve that tells me what's the maximum step size as the analysis is progressing. So I'm going to therefore select my load curve again. This time, if I expand the steps, I will see that there's an option for the must points. So by default, in the must points, what I have is that, you know, the time increment is going to be 1 second up to time 1, and then remains 1 second for the rest of the analysis. This is obviously not appropriate for what I want to do. Remember, I'm applying 50% compression in 1 second. So I would like that first, you know, during the first second, I should have no more than 0.1 second increments. And then, you know, I'm going to compress, and it's going to relax really quickly. The first second right after I finish compressing is probably going to relax the fastest. So I should probably keep a pretty low, you know, time increment during that second as well. So I'm going to have at time 2, I'm going to have exactly 0.1. Okay. So now you might say, well, if I was going to click this point here, why did I click this one as well? The answer is because this is the end of the compression ramp. I want FEBio to stop exactly at this time point. I want to make sure that I get the solution at this time point, so I include it as a must point. This is important. Now, starting from, you know, this, second, I could say, well, maybe for the remaining up to 10 seconds from now, from time 2 to time 10, maybe the time increment could be longer, because remember, the stress relaxation response was exponential. So that means that as time progresses, I can take larger and larger time increments. So a good rule of thumb that I have found for biphasic materials, when you're doing an analysis like this, so you don't have dynamic loading that's continuously loading. If you had dynamic loading with a cyclical loading curve, then your time increments should not change too much over time. But this is specifically stress relaxation. So I'm going to have the time increments increase in a logarithmic way. It's the choice that I make. So Until time 10 seconds, I want 1 second increment. Until time 100 seconds, I want 10-second increments. Until 1,000, I want 100, 10,000, 1,000. And because the analysis runs to 50,000, I'm going to allow it to go to 100,000. So I'm going to add one more time point, but this time I want the increments to be linear. So that means I should put a linear curve. And this last point here, I want it to be, well, actually, before I do, I'm going to change this point in a moment, but because I changed this from step to linear, I'm going to go back and make sure that my time increment at time 0 is also 0.1. This way I have a constant time increment for the first 2 seconds. And then up until time 100,000 seconds, which is 10 to the 5, I want my time increments to go linearly up to an increment of 10,000 seconds. You see? So now if I zoom out on the load curve, you can see that my time increments will increase linearly, which means for every decade in the time response, I'm going to have the time increment increase by also a decade, but a factor of 10 less. Okay, I hope this was clear. If not, you can ask questions, in the chat box, and we will answer it. So I'm ready to run the analysis. So I'm going to say, so I saved my analysis, although when you do a run, FEBio will automatically save the last version. And I'm just going to click run here. And I'm going to wait for the solution. And, it's progressing, hopefully, if I didn't make any errors. See, even though I'm running a pretty large number of time increments, it completed the analysis. I'm going to look at the results. So the first thing I'm going to plot is the effective fluid pressure, because after all, this is a biphasic analysis, and so we care about the fluid pressure probably more than anything else in terms of if I were to compare this to a simple elasticity analysis. So time, the time is 0. I'm going to just look at the fluid pressure immediately at the first time increment, which happens to be at time 0.1 second, and I'm like very disappointed. I see that the fluid pressure is oscillating, and this is a really frustrating thing. So I'm going to show you in a moment what that fluctuation is, but let me click on a few more time increments. Remember, I'm applying the displacement, I'm compressing by half of the thickness in 1 second. So this is at time 0.9 and 1. The oscillations are still very obvious, but they seem to have decreased here. Let's go a little bit further. As I advance the time slowly, it's only like 2 seconds, maybe up to 10 seconds of the analysis. Eventually, it looks like the pressure becomes more or less uniform, right? So it looks okay now. So the solution looks very reasonable starting from this point. And in fact, if I play the rest of the analysis, it looks very clean. And I should walk away thinking to myself, this is perfect. But I am a bit upset about the oscillation in the fluid pressure at the beginning. And I want to say that this is not, a coincidence or just bad luck. It's because I picked a mesh that's uniform in the radial direction, but I have the fluid pressure has to drop to 0 right here at the edge because that's my boundary condition. I have an essential boundary condition that says the fluid pressure is 0 here. And yet I have a pretty coarse mesh as I approach this boundary. Let's take a look. There are different ways. I'm now highlighting some of the features of FEBio, Studio. And so I'm going to select an orthographic projection, and I'm going to look at it from the right. And then I'm going to select the nodes, and I'm going to go to the first time point. And I'm going to rubber band around this corner here so that I can select only the nodes that are located in the radial direction. Then I'm going to say post, new graph. And I'm going to select a time scatter. I'm going to plot the effective fluid position against the current position in the x direction because I selected the nodes that vary along the x direction. And when you select a time scatter, it'll plot a set number of time increments. So they happen to be from time 0 to about 3.4 seconds in this particular case. So what you can see is the fluid pressure at the center is rising as you apply the compression. Remember, the compression ends at time 1, which is the gray curve that you see here, right? But clearly, as you approach the edge, you have these oscillations, and that's because the mesh is coarse. So this is a typical feature anytime that you have a zero fluid pressure boundary in a biphasic analysis. How do we resolve it? The answer is you actually need to use a biased mesh. You don't have to change the number of elements. I have 20 elements in the radial direction. I just want them to be thinner, close to the radial edge. And luckily, I can do that very easily here by introducing a bias. I want as the radius increases, I want the elements to become smaller and smaller. So I want a bias which is less than 1. It's the multiplication factor, if you want. Each element becomes smaller than the one before it. So I'm going to pick a value of 0.85 because that worked fine for me before. And I've biased the mesh. And I'm going to rerun the analysis. And, because it's exactly the same number of elements, the time it takes to run the analysis should be more or less the same. And now this time, if I display the fluid pressure at the very first time step, so I'm going to just go back to the perspective view. I'm going to look at the first time point. Look, at time point 1 second, I have nice uniform fluid pressure and it drops suddenly here. Why? Because I have a very fine mesh. So this is an important result that I want you to appreciate for biphasic analysis. Okay, so biasing the mesh is important. There's a couple of other things I want to illustrate for you related to this problem, but essentially we've solved this problem. So if I animate this, we get the complete response. And of course, if you want to look at the fluid flux, you can click on this, icon here. You select the fluid flux from here, and then, you can either auto scale it or you can scale it until you actually see some arrows showing up, you see. So that means, I have a scale of 1,000 here. And so then if I continue the animation, the arrows decrease in size. So maybe I can use an even larger, so it's easier to see. At the very beginning, you're going to get large arrows. The fluid is squeezing out because the pressure gradient is very high. So Darcy's law is ejecting the fluid, at a large velocity. But as the fluid leaves, the tissue recoils because you have to conserve the volume. You're losing fluid volume. That means the mixture volume has to go down. And in the end, I'm going to recover the initial. Okay, so that's an important thing. So remember to bias the mesh. But before I leave you here, I'm going to illustrate one more, interesting tidbit. Remember what I told you, that we have a permeability that varies with the relative volume. So if I actually, and I forgot to, show you how. So let's go back here, and I forgot to show you how we can add more plot variables. That was an important thing. So I want to add the relative volume. I want to add the fluid pressure. Not that I'm going to talk about it much, but it was in my slide. And I'm going to add the porosity. Okay. So I've added these, and I'm going to rerun the analysis. That's the problem. If you forgot to add a plot variable, you actually have to rerun the analysis. We're very lucky here that the analysis runs very quickly, but if you were unlucky, it took 3 days to run the analysis and you realize you forgot to output something, remember that beforehand. So now what I'm going to do is I'm going to look at the relative volume. And what you see is that the relative volume decreases near the edge while it remains constant here. So that means that the permeability is going to decrease here. Remember, it's an exponential function of j squared minus 1/2. So the permeability is decreasing, but I don't know the permeability here. All I know is j. So I can plug this value of j back into the formula from the user manual, or I can actually choose to output the permeability tensor as a plot variable. Unfortunately, as of today, it's my fault. I forgot to add the permeability as an option in the list of plot variables. If you type permeability, you're not going to find it. But it is implemented in FEBio. So I'm going to show you if there is a feature like this that you're told on the forum, by the way, there's an undocumented feature and you want to implement it. One option is to go ahead and open the FEB file, which in my case, remember, I actually placed my file on my desktop, and I go to the jobs file, and I'm going to open this file, which for some reason it's not letting me open. Sorry, I'm going to try this again. Not sure why it's doing this. Okay. There we go. It's related to my operating system. Don't worry. And then instead of importing it as a model, I'm going to edit it as a text file. Then I'm going to scroll down all the way to the bottom, and I'm going to manually add a plot variable called permeability, which is, as of now, an undocumented and hidden feature. So, of course, we will document it in the future, and we will add it to FEBio Studio. But for now, it's just an illustration of how you can edit the file, and you can run it again. And when you do, then it's running the file that's currently active in this window. And then you're going to plot the results. I didn't change the file name, so the results are here. But suddenly, the permeability is available as a plot variable. Remember, this is an isotropic permeability. So if I look at any of the principal values, they should be the same. And you can see that the red region is the value that we entered, 10 to the -3. That's under when j is equal to 1. And here it's smaller. So I'm going to select this element at the radial edge and this element, at the center. And I'm going to say post new graph. And I'm going to display this permeability. And again, any one of the principal values should be the same. And lo and behold, you can see that it starts out for all of the elements at 0.001, which is the K0, the permeability under 0 volumetric change. But because we have an m equal to 6, a very strong nonlinear response, in this case, the permeability drops to almost an order of magnitude below. So you can see why it took 50,000 seconds for this analysis to equilibrate, because the permeability went down. So it became harder and harder for the fluid to escape from the radial edge as the porosity decreased. Okay. So, which, by the way, you could also look at the porosity, since I requested to output the porosity. And this is how the porosity decreases. It's not the same response because it's not the exponential function that we have in the permeability. But you can see the porosity decreases across the board. Very good. So this covers the demonstration that I wanted to give you. Now I'm going to switch back to my slides, and I'm going to talk about some of the important reasons why biphasic analysis is important for modeling biological tissues, in contrast, let's say, to an elastic analysis. So this is the response for the mixture stress in the first principal direction, so the maximum direction of principal stress, which in this case is going to be radial or circumferential. Okay, so what we see is that if you look at this, sorry, I have the Zoom window is in my way, so I've got to move it out of the way. So what you see here is that these two blue colors are negative, the rest of the colors are positive. So what we see is that the stress is actually, even though it's the maximum principal stress, it's actually compressive here, and it's tensile here. So you might think, aha, the tissue is in tension here, but it's in compression here. But remember, you're looking at the mixture stress, and this would be the stress that you would find if you did an incompressible elastic or uncoupled, elastic formulation. But in a biphasic material, part of this negative value comes from the fluid pressure, which is very high near the center and approaches 0 at the edge. So you might be mistaken. You think that the solid matrix is in compression here, but it's not. Why? Because if you look at the fluid pressure, it's very high in magnitude. But if you plot the principal solid stress, so the principal value of sigma E, you see that it's in tension everywhere. Everywhere it's in tension. So when you do biphasic analysis, you get insights into the mechanics of a tissue that you would not get if you did an elastic analysis. Let's say that you're interested in tissue damage. Now, the tissue damage only occurs in the solid matrix. You're not going to damage the fluid, right? So you shouldn't be looking at the total stress, because then you would conclude, oh, the tissue is perfectly safe here. Nothing's going to happen. If it's going to fail, it's going to fail here. But in fact, it's got high tensile stresses here as well as here. So it's kind of important to keep in mind that the biphasic analysis gives you insights, beyond just, oh, I can tell where the fluid is flowing. It's not just that. The fluid pressurization can shift the load away, like when you compress it, it can shift the load away from the solid. And so the solid matrix in this case is always in tension. That's why a biological tissue like cartilage is fibrillar. Its solid matrix is made out of collagen, even though cartilage is loaded in compression most of the time. That's because it has to resist that lateral tension. Okay, so I mentioned boundary layers a moment ago. when I displayed that particular unconfined compression result. This is the fluid pressure when you actually meshed. And you can see the boundary layer is this region here, this narrow region where the fluid pressure changes rapidly. Over time, the boundary layer disappears. But remember to use a biased mesh to capture the boundary layer. So we've talked about this. The other thing I wanted to mention is that, it's not just an unconfined compression. This is a confined compression problem with only 10 elements through the thickness, but they're hex 20 elements. And you apply a constant stress because you want to do a creep experiment, but the fluid pressure is 0 because you're applying the load with a porous filter. Then if you look at the very early time response, you get this oscillation in the fluid pressure, which actually is very strong and propagates all the way to the center, to the bottom of this particular, confined compression analysis. But if you use the exact same number of elements, but you bias them, then the fluid pressure is going, you're going to capture that boundary layer very nicely. And this issue with boundary layers only occurs in the early time response. I showed you how to create a bias if you've created your geometry within FEBio Studio, but what if you import your geometry? Let's say this is the tibial cartilage from the open knee project, from one of the models of the open knee. The models use elastic models for cartilage, but what if you wanted to actually convert this to do a biphasic analysis? You need a biased mesh near the articular surface to capture the rapid change in fluid pressure when you apply the load. Luckily, we have a boundary layer tool, which is available to us. You select the surface, you select the amount of bias, how much do you want each element to increase in size from the selected surface to the inside of the mesh, and how many elements do you want to add? In this case, I selected 2 and 3. So that means that the first layer is half as thick as the second, which is half as thick as the third because of the factor of 2 here. And of course, you can select other surfaces. In the case of articular layers, you can have large shear strains at the cartilage bone interface. So it's not a bad idea to also bias the mesh at the bottom. You can use this tool across the board. I've mentioned the concept of short-term response. And so how do you determine what is a short-term response? Is it 0.1 seconds? Is it 1 second? Is it 0.01 second? Well, it depends on the properties of the tissue and how you're loading it. Like everything else in mechanics, you shouldn't do a finite element analysis unless you have a good sense in advance of what you expect. Otherwise, how would you know how quickly you should apply the loads, how large the loads should be, et cetera, et cetera. So the same is true. You need to do back of the envelope calculations for biphasic analyses. The characteristic time constant for fluid flow in a biphasic material is proportional to a characteristic length, squared, divided by characteristic modulus times the characteristic hydraulic permeability. The length, the characteristic length, is the distance that the fluid has to travel from the high pressure to low pressure. So in confined compression, the fluid is it's the thickness of the sample, because the longest distance it has to travel is from the bottom of the sample to the surface, so it's the thickness. But in unconfined compression, it's the radius, because the fluid is traveling in the radial direction. The characteristic modulus, again, it's either tensile or compressive. In confined compression, the tissue is in compression only, so you pick the compressive modulus. But if you have a fibrillar tissue like cartilage, for example, its tensile modulus will be much larger. And in unconfined compression, the direction in which the fluid is flowing, the radial direction, is going to be in tension when you compress the tissue. So you would have to pick the tensile modulus for the characteristic time constant in unconfined compression. And K, it's fine to pick the initial value, because initially there's going to be very little change of the volume ratio J. So the time constant is going to be usually estimated reasonably well with K. But if you have a strong decrease in permeability as the analysis progresses, then you saw the stress relaxation analysis that I had. It took 50,000 seconds and maybe even longer to reach steady state. If I had picked a constant permeability, I could have reached steady state in 10,000 seconds. So you have to keep in mind that this is an approximate relation. And the short-term response is when t is much smaller than tau. So if tau turns out to be 1,000 seconds, then much smaller, t would be 1 second or 0.1 second. And so that means that the interstitial fluid has had very little time to diffuse out. And that means that the biphasic domain volume is nearly preserved. We call this an isochoric response. It could be that the volume of each element is conserved, but not necessarily, and I want to illustrate this. So here's the unconfined compression problem. And remember, the relative volume here, in the early time response, the relative volume is quite uniform. It's only over time that, right here at the edge, you're losing fluid. But because the relative volume is uniform, that means each element is more or less conserving its volume. So that means that if I were to select all the elements and integrate the relative volume over all the elements, I can get the total volume of the tissue. And of course, over time, over 50,000 seconds, the volume is going to decrease. You can obviously see it. Here's the undeformed configuration. The final configuration is, half the size. So the volume went down by, a factor of 2. But if you focus on the first 10 seconds of the analysis, then you see that the volume changes very little. So that would be the early time response in this particular case. Now, you can also seal the boundaries. So this is a cantilever beam problem where you've sealed the boundaries. And when you seal the boundaries, the fluid cannot leave. When you do the analysis, you can still have local variations in the relative volume. So even though the total volume of the beam is conserved, locally the fluid is escaping from this blue region and is flowing into this red region. So even though you're doing the analysis without allowing the fluid to leave, you actually have, local variations in the element volume, but the total volume that you can evaluate easily by integrating the relative volume over the entire domain remains constant. Why? Because the fluid cannot escape. So this is important. That means that a finite element biphasic analysis with sealed boundaries, for which you don't need a biased mesh, right? If the boundary is sealed, then there's not going to be a boundary layer in the fluid pressure. Then you can use a uniform mesh. Then you can do the same type of analysis that you normally do with an incompressible material. But it's important to understand, contrary to an incompressible material where J is going to be equal to 1 everywhere, in a biphasic material, even though the total volume doesn't change locally, J can decrease in some places and increase in other places. Okay. So when should you use a biphasic material? Whenever your tissue contains a significant amount of fluid, which means most biological tissues, when you're concerned with how much load is supported by the solid matrix versus the fluid. So this could have a significant influence on the failure response. And obviously, if there is flow through the porous matrix and you want to know the time-dependent response, then you should definitely use a biphasic analysis. So anytime that you need to test a hypothesis that's related to interstitial fluid pressurization, you should use a biphasic analysis. So that completes my presentation for today. We're going to have future seminars on biphasic materials. We can talk about a variety of things that I didn't cover today. There are more types of boundary conditions that we can prescribe. We can look at the role of fibers. I mentioned how, tensile response, compressive response, that would only be achieved if you add fibers to your solid matrix. If someone is interested in body forces, let us know when you fill out the survey at the end of this webinar. And, if, you want to do a creep problem, you often have to do frictionless contact with a rigid and permeable solid, or permeable for that matter. And generally, if you want to do biphasic contact. And then we introduced very recently, we just published a paper on hybrid biphasic materials. Actually, if you don't want to neglect inertia terms, you do want to do wave propagation through porous media, we can talk about biphasic materials. I'll remind you that this is a team effort. The current team members are shown here. You've already heard Steve give the first 3 webinars, and Dr. Weiss and myself are the PIs on the NIH funding that we get to support this effort. And Dr. Ben Ellis has been on this project from the very beginning, and Mike and Raul joined more recently. And these are the resources available for you. I'm going to keep the slide up, and now I'm going to answer whatever questions you have that haven't been answered by people on the panel.
So Gerard, I think I've been able to keep up with most of the questions while you were talking. If you go to, while people are thinking about what other questions they might want to ask you, if you go to the dismissed panel, you can see a couple of questions that that you might want to just double check my answers.
Okay, very good.
Maybe John Bracamonte about the zero Poisson's ratio for the solid phase.
Right. So the Poisson ratio represents how much lateral expansion do you have after the fluid pressure has gone down to 0. So that's the definition of the Poisson ratio in a biphasic material. It's not the Poisson ratio when you first load it, because when you first load it, the volume is conserved, so the tissue is going to expand. So really, Poisson ratio is a measure of the compressibility of the pores. And Experimentally for cartilage, for example, we've measured it to be 0.02, 0.06, 0.1, depending on which zone of cartilage through the depth. So for illustrative purposes, I just use 0. But it would be inappropriate to use a value of 0.4, 0.45, because you're saying to yourself, oh, but I want to model my tissue to be nearly incompressible. If you want it to be nearly incompressible, just seal the boundaries. If you want to use a biphasic analysis, just don't prescribe a 0 pressure. Then the Poisson ratio is going to affect how much shifting of the fluid occurs from one location to the other. Obviously, if you pick a Poisson ratio that approaches 0.5, then even the pore volume cannot change, which means even internally the fluid cannot shift. So that cantilever beam problem, then we will get mesh locking in that case if we allow the Poisson ratio to be close to 0.5. So one should not use value of 0.5. In that case, just do an uncoupled structural mechanics analysis if that's what you want. If you want 0 change in volume in every element at all times.
Sometimes I think about this in terms of the solid volume fraction. I mean, you could have a material, if the material were 100% solid, right? Maybe it has a Poisson's ratio of 0.3, but if the material is like most biological materials where it's 10 to 20% solid fraction, then obviously, the influence of the filled solid, Poisson's ratio on the observed, Poisson's ratio of the skeleton, it becomes so small,
Right. Yeah, it's a reasonable way of looking at it. I see here that Nurul Karim asked, is there a way to estimate permeability directly from a geometry using CFD simulation inside FEBio, similar to Palabos? The answer is yes, but not using the biphasic module. We have an FSI module and a biphasic FSI module, but really what you want to do is an FSI module where you create a solid structure which represents the porous structure. So you explicitly model the porous structure, and then you put a viscous fluid in it, and then you apply a pressure upstream and you measure the flow rate. Then you extract the hydraulic permeability. So the answer is yes, but not using the presentation I showed you today. It would be a different lecture. It would be a webinar on fluid structure interactions.
So it looks like there are a few open questions now that have come in since we started talking.
Okay. Can you build models of multiphasic materials with multiple layers of materials to study fluid pressure-induced deformation in the second layer? So again, my talk today was about biphasic materials, but yes, you can create heterogeneous materials in FEBio without any difficulty. That's definitely, a possibility. So let me know if I didn't answer your question correctly. And is it possible to model the flow through the porous material driven by a boundary fluid pressure difference? Yes. So that would be a permeation analysis. So depending on how you set up the boundary conditions, permeation experiments can be done either by clamping your tissue between two porous filters and applying a pressure gradient, in which case the boundary conditions I described today are sufficient. But if you actually don't clamp the tissue, if you just prevent it from moving, let's say downstream, but upstream it's free and the fluid is flowing through it without a porous filter, then you need some of these more elaborate boundary conditions, the mixture velocity boundary conditions that I listed as one of the optional things that we can cover in another seminar. And John Peloquin, you said, regarding the oscillations of fluid pressure in the uniformly spaced mesh, is it possible to correct this by other means, such as a different solver? So yes and no. So people who've done porous media theories computationally have long suggested different ways. So there are what we call stabilization methods, where you artificially introduce a parameter in your equations to minimize the oscillations. So we actually have an undocumented stabilizing factor that we can use. However, when we compare the results to a biased mesh, we don't get the exact same results. So it's a kind of a hit or miss. You're playing with that parameter, which is the stabilization parameter, and you can keep increasing the parameter until you get a smooth response, but you don't know if that smooth response is correct. So that's one limitation. Another approach which we have tried and is available is to use a hybrid formulation for the biphasic elements. So we use second order displacement interpolation and first order fluid pressure interpolation. That's a more conventional approach in porous media mechanics. We've implemented that. It reduces the oscillations but doesn't eliminate them. So far, I think the best solution is to just bias the mesh, because then you know that the solution is the correct solution. Any stabilization method may give you smooth results, and there are more papers in the literature that have been brought to my attention that don't require any user-specified parameter for stabilization. I haven't implemented those yet, but I will, and I'll try that, but I suspect that the answer is going to be the same. You will not be certain for a given problem if that stabilization is giving you the correct solution. Okay. So I think did I dismiss any question by mistake? I hope I didn't. There were 4 questions, but then I answered only 3. Let me see.
I think one was maybe a thank you or something like that.
Okay, very good. Anything else? Adaptive meshing. Oh, but you answered that, Jeff, right? So Todd, hey, Todd. So adaptive meshing is under development, is currently available, but I haven't used it much, but Steve can provide, can probably give a webinar in the future on that. My contact email address has been provided to you. Sorry, I'm going through these. I'm going to stop in case there are any more questions. If not, I think we're almost out of time. Jeff, any suggestion at this point?
No, I think we're in good shape. That was really informative, and I hope the audience has got a good handle on how to get this get started with biphasic materials. I think it's safe to say there'll be some follow-up webinars that will address other aspects of biphasic and multiphasic materials, and those will be coming in the near future. Stay tuned to our Twitter feed. You'll hear about them there as well as on the webpage.
Okay, so Steve, you can end the meeting on your end, I think. Goodbye, everyone. Thank you for joining us today.